a waking up call. So we'll separate you from your dinner. So I try to be, well, maybe entertaining, I don't know, let's see. My name is Irene D'Amico. It's a pleasure to be here. Let me thank the organizers for this very interesting conference, very varied, lots of interesting input, and also for giving me the possibility of presenting you this work today. I appreciate to have the microphone on here because I can move around, I move a lot around. Hopefully this also will keep you awake at this time. The work I will present has been done in collaboration with Elliot Fox, Marcel Herrera, Taisa Menses de Mendoza, and Ferdinand Schmidt-Kahler. I'm from the University of York, and this is an international collaboration. I will be talking about small, just few qubit thermodynamic machines. During this conference, we already heard about quantum thermodynamic machines. And in particular, in a talk yesterday, there was an emphasis on, for example, using these machines to the advantage of quantum computers, so embedding these machines in a quantum computer. Here, the idea is to use actually a bit of a small processor of a quantum computer, and a specific gate within that quantum computer in order to create these quantum machines, quantum thermodynamic machines, and as I hope I will be able to show you, or to convince you of, also get some quantum advantage for these machines. So, as I said, we are going to use quantum processors as quantum thermodynamic devices. And we will be using coherences as a quantum resource. And I will be showing you that the use of coherences will allow us, for these specific devices at least, to boost the performances of quantum batteries and the performances and efficiency of a heat engine. Both works have been published. As I said, we are going to talk about small quantum processor, just 2 or 3 qubit quantum processor. And the idea is that we are bounded by using a single gate in order to implement, like an algorithm, this machine, to charge the battery or to do our working cycle. The particular gate we are going to look at is an n-root CNOT logic gate, and let's see, this hopefully is, no? Yes. Here is the matrix for it. And the idea is that if I apply n times this gate to the same couple of qubits, and with the control and the target being the same, I will perform after an application, a full CNOT gate. When Ferdinand proposed me this idea, 2, 3 qubits, this type of gates, I thought, oh yeah, of course, this is just an 8 by 8 density matrix. We'll have all the results in a week. Little I knew, the problem is actually has a lot of parameters. It took us much longer to do the calculation and also really to appreciate the complexity of it. And so that's the story I'm going to tell you. So first of all, I will start from the batteries. So our device is a battery. And again, the idea is that I have 3 qubits. In their initial state, they are disentangled. There are 2 qubits that I will call A and C that are initialized in a Gibbs state. And then we have qubit B, which is actually initialized in a pure state. So we have quantum coherences here, and this is our resource. And we will treat this initialization as a free resource, okay? The protocol, as I said, this is a problem in which you can actually open a whole Pandora vase. So we had to choose which protocols to use. And we settled down for 3 protocols. So 2 qubits and 3 protocols make six cases. But anyway, the first protocol will have as control gates the case in which we always have the upper qubit, upper in this sense, ABC, as a control and the lower as a target. The second protocol, we invert it. Target is on top and control is the second one, I mean, in the row. And then the third, symmetrize them. And then the idea is that each of these is en route control not gate. So the idea is that we can apply this that we call an iteration, this protocol here, this little algorithm here, as many times as we want, so m times, and every time we can check if we get a good performance from our system. We are dealing with batteries, so a typical measure of performance for batteries is ergotropy, which is the maximum amount of work that one could extract from the system using cyclic and unitary operators. So basically leaving the system in a passive state after I've applied an appropriate unitary operation. And so I will directly go to the results. And I will only present results for simplicity for the 3-qubit system. So the 3-qubit system, this is the type of, again, iteration. So for every iterations are here on our y-axis. For every iteration, I apply, you see how many gates, depending on the case 1, case 2, case 3, I lost the arrow, case 1, case 2, case 3, and we calculate the ergotropy. On the x-axis, I have the theta, which is used for the initialization of qubit B. Qubit B is the one that is initialized in a pure state, so its state is defined by two angles, theta and phi. So theta here, we vary. Phi is fixed at pi. Qubit A is at higher temperature. Here is initialized at higher temperature than qubit C. And qubit B, the internal energy will vary as I vary the initialization, the two angles in the initialization. So we see, okay, lighter color, we get more ergotropy. So we see, okay, maximum ergotropy here we find for case 1, for theta close to pi, maybe even pi, so this would be simply inversion population. However, one could ask, this is a complicated system, we have different protocols, different cases. Is really ergotropy a good way of comparing all these cases and devices? It really depends on what you want from the device. So, first of all, we remind to ourselves that our initial state is not passive, so it's not really fair to simply look at the ergotropy of the final state to define the performance of my system. A fairer way of looking at the performance of my system is actually considering the gain in ergotropy, so the final ergotropy minus the initial ergotropy. And when we look at this, we find that actually the values for which we get the maximum gain of ergotropy correspond to the case in which actually I have initial coherence in the system, and this is actually really the region of maximal gain of ergotropy. Here you see it less, and also you can see it here. Another measure of performance that the other thing one could notice is that we have charging and discharging regime. Again, we are increasing m as we go from 0 to 30 on the y-axis. And you can see that first we charge our battery, then if we don't stop, actually we would discharge our battery, we would discharge our battery. So this is also an interesting point. And the other point to notice is that the application, the use of this en route control NOT gate allows us for a fine-tuning of how much ergotropy variation or ergotropy we actually put in our battery. So we can really charge our battery, or if you want, gain as much ergotropy as we need for the job we want. So we have this fine-tuning given by the type of gate that we use. Another type of question you can ask, though, is not just what is your gain in ergotropy, but also with respect to the final energy that I have in my system, which is the fraction of energy, so that I can actually extract from my system, so this ratio here. And this is the answer for, again, just the 3-qubit system. And you can see, again, there is importance from the, also here, I don't know how to go backward, voila, from the coherence, initial coherence, depending on which type of protocol I apply to construct my, my system. And so we see that it would be interesting to actually combine these different measures of efficiency for the system. And so what we propose as a figure of merit for an optimal battery is the product of the gain in ergotropy that we have to our process, and this energy ratio that we can extract, so the ratio of energy that we can extract as work at the end. And when we look at this, again, we find that indeed initial allowing as free resource initial coherence is just 1 qubit of the 3, increase dramatically, the efficiency of our device, depending, again, also on the number of iterations. So if we want to get the maximum ergotropy, we know now which is the initial state we can choose and how many iterations, so how many times we have to apply this, this minimal protocol. But here I have looked just at the case in which phi for the qubit beta, the qubit B as initial state is equal to pi. So let me now show you the whole results. So this is the best ergotropy overall over all the, sorry, we go back, over all the 30 iteration and over all possible initial state for qubit B. So this is phi now, and this is theta. This is the 2-qubit circuit, which I haven't shown you results so far. This is the 3-qubit circuit. And this allows us actually to identify and to compare all these different systems and protocols and say that, at least for this type of device, we have a marked dependence, first of all, on initial condition. The best overall device is the one with 3 qubits and using this simpler case 1 type of minimal circuit. And indeed, we can see quantum advantage from initial coherence in our system. Just to stress this, here we have compare our result for all cases 2 and 3 qubit systems in comparison to the case in which we initialize also qubit B in a thermal state. So now we have all the 3 qubits initialized in a thermal state, and these are the red and yellow dots. The light blue dot are the case in which we have only 2 qubits, so qubit A and B as initial coherences. The blue dots are the diamonds, are the one in which initial coherences are allowed in qubit B, and we have 3 qubits. And this allows us, all this comparison, to identify for this device as a quantum battery and this set of algorithm for charging the battery with this specific gate, an overall winner. So to compare really all these different cases and number of qubits and different, as I said, protocols. Okay. The second part of the talk will use the same working fluid, but we'll look at it as a heat engine. And what we see in this case is that the fact of allowing qubit B, again, just 1 qubit, to have initial coherences as a free resource allows actually to improve a lot the efficiency of our devices, reaching even 100% efficiency. So, again, this is our heat engine. This time, qubit A and B are initialized at the same temperature in a Gibbs state. Qubit B is initialized as a pure state. This is my initialization. Initially, the qubits are non-entangled. They will, in part, gain entanglement through the application of the gates. So this is the iterative protocol application. This is basically our work production cycle. And what we will look at is at the end of this work production algorithm, what is the amount of extractable work that we can get at the end. And once more, these are, we will just look at 2 cases in this case, and these are the type of algorithm that we will apply. They are 2 of the same algorithm that we have seen before. So first of all, we can compare all these algorithms and number of qubits versus the initialization temperature of qubit A and C, and we see that there is a saturation of work. We extract the maximum extractable work. This is done over all possible initialization of qubit B, and these are the best type of algorithm and number of qubits. They are here up. And so next results will be shown for this particular value of temperature for qubit A and C. And we have here the maximal extractable work over 150, m equal 150 under all these cases. And now we will look at how going through the here through the line of maximal extractable work, the work itself behave and the efficiency of the machine behaves. So these are cuts of what I showed you before along the, for each case and each number of qubits in the system along the maximum extractable work. This is the number of iterations, so m, and these are 150 iterations. This is pink is the extractable work. You see that is oscillating, so I get maximum work, for example, and then I go down again and so on, and this is more complicated and so on. And blue is the efficiency. So one thing that immediately we notice is that maximum work, I lost again the arrow, always correspond to very high efficiency. Here, you can see it here, you can see it there. And so the efficiency corresponding to maximal extractable work can be even 100% up there, but anyway, it's always extremely high, 97, 93, 84. Our definition of efficiency is the standard one, it's here. So is the extractable work divided by the energy absorbed by the hot component of the working medium under reinitialization. And just as a comparison, we can say, okay, is this an advantage given by coherences, so by quantum coherences? Well, in 3 cases out of 4, indeed, this is the case. And the advantage that we get can be up to 28% for this case here. And so again, we see that having quantum coherences allowed as a free resource for just 1 qubit can dramatically increase our result for this quantum thermodynamic machine. Which brings me to the summary. So we have a quantum advantage from initial coherences in just 1 qubit. It's interesting, we have finely tuned output from this machine because we use this trotterization of the control knot, if you want, as the single gate to operate the algorithm that either charge the battery or run the engine. We have discussed various measures of efficiency for the battery. In general, this confirms that we have a quantum advantage from coherences. For quantum engines, we have a very high efficiency at peak extractable work and an increase of maximum work production and also work parameter region for 3 cases out of 4. What is interesting, and I have not discussed, is that we find a linear correlation between the extractable work and the mutual information. And when we try to look at which component of the mutual information is the important one, so is the classical or is the quantum discord? Well, it's the classical, contrary to what we would have guessed, because this is a type of gate that produces also entanglement. We find that, in general, the best correlation is with the mutual information, should read mutual information. So the best linear correlation is between extractable work and mutual information. And is, again, the classical correlation part, the one that seems to be best correlated with the production of work. And this is my last slide. So thank you very much for your attention.
We're running quite a bit of time late, so there's no time for questions, but feel free to come talk to Irene directly if you have any questions. So let's thank Irene again.
Thank you, everyone. This was an intense day. It was the most intense of the conference.